Now we solve the truss problems, particularly to find the deflection using the virtual work method. Now this is the energy methods. This method is used to calculate the deflection at any point in the truss, unlike the previous method for strain energy and external work done. Now let's has a problem here. It has a truss, there's a pin connection here, and we have the truss members, and it has a external load applied 100 kilonewton at point P. We have point A, which is pin, point D, point C, and the distance between these two is 2 meters, and distance from here to here, these members are each 2 meters. Now the question is to find the vertical displacement, at C. So we need to find the vertical displacement at C due to this 100 kilonewton load. Now we need to use this virtual work method. Another data is given, Young modulus times area for all the member is given 80,000 kilonewton. That is given in the questions. That is for all the members, member A, maybe member BC, member CD, and member AB. Now we're going to solve this example in the 4 steps. So step number 1, we use the virtual system. Let's say we apply the virtual load. Second steps, we going to do the calculations of axial force, let's say small m due to virtual load 1 kilonewton. Step 3, we going to calculate axial force, and that is capital N. Now capital N represent the due to real loading on the truss. And the step number 4, we're going to find the deflection at point C. So these 4 steps we're going to follow. So let's draw the virtual system first. Now how we can draw the virtual system? It's very simple. So we draw exactly the same given in the problems, but the difference here that we removed all the loading, external loading, D, let's say A, B, and C. Look at these pictures. We remove all this one. Now we like to remove these 100 kilonewtons in the virtual systems, and we need to apply this unit load. Please note, this unit load is applied where we need to find the deflection in the direction. So in the question it says that find the deflection at point C. So we need to apply the virtual load at point C. So that's the first steps that we need to draw the virtual load, and all the measurements are still the same, 2 meters, and we have this distance 2 meters, and this distance is 2 meters. Now step number 2, we need to calculate the internal forces in all the members due to this virtual load. So we can use the joint method. Let's say we use joint A, or let's put the joint B first. That's the easy one. So if I draw the joint number B here, and if I have a force of, let's say, BC and force of BA, I can see there is no load at B, and it has a 2 members are connected at B. Now this is the perfect recipe for 0 forces. So you can see these are the 2 member joints, and there is no load at point B. So FBC equal to 0 and FBA equal to 0. So that is simple. Now we can take the joint C. Now let's draw the joint C. Now this joint C has a, we can draw the joint C, and now joint C has a virtual load. So let's say this is joint C. Now this is 0 force member, so we don't need to draw this one, but let's draw it out first. And we have force AC, and we have this force is CD. That's for CD, and we have virtual load 1 kilonewton. And please note, this is the triangle 2 meters 2 meters, so you can see this is 2 meters and 2 meters high for these members. Now, and then if you take this one square root 8, because that would be 2 square plus 2 square equal to 4 plus 4, it gives us square root 8. Now in this case we can redraw it, let's say without this zero member. So we have this force here, and this is FCD, we have 1 kilonewton, and that is point C, and I just remove this zero force member, and FAC 2 square root 8. Now let me redraw this one again by changing this diagonal to its vertical and horizontal component. That will make easy. 1 kilonewton FCD, and because of this one we have this FAC times 2 on square root 8. That 2 is coming from here and square root 8 coming from here, and we have this force going along this horizontal, which is as well FAC times 2 on square root 8, which is this 2 and the square root 8. Now we can apply some of the force in the x direction equal to 0, left to right is positive, or we can apply it first vertical equilibrium, upward is positive. Now in this case we can apply the vertical, 1 is going down, so minus 1, FAC going down, so is minus FAC 2 on square root 8 equal to 0. We can bring this minus across, so minus FAC times 2 on square root 8 equal to 1. So FAC equal to, we can bring this minus across, and then square root 8 on 2, that give us minus 1.41 kilonewton. And then similarly we can apply some of the force in the x direction. FCD is going left, so minus, and this minus FAC times 2 on square root 8 equal to 0. Now we substitute FAC is this value, so minus FCD, this instead of FAC I can put minus 1 times square root 8 on 2 times 2 on square root 8 equal to 0. So we can cancel 2 square root 8. We can have minus FCD, minus is plus 1 equal to 0. So minus FCD equal to minus 1, FCD equal to 1 kilonewton. So that's the second force that we found. I think we almost find all the forces. Let me put that one in the diagram here. We have this pin here. We have a load. We have A, we have B, we have C, D. Now this is 0. This is 0. FCD is 1 kilonewton. So FCD is 1 kilonewton, and FAC is minus 141. So minus 141 kilonewton. So that is the due to this virtual load that we place onto the system. Now we need to repeat the same procedures for the real loads. So for the real loads we can take the next video to find the step number 3. We need to find the axial force capital N due to real loading. Okay, so that's we're going to take in the next video. Thank you.